Hello friends, welcome to the session on support vector machine. You already seen neural network and mostly the main application of neural network is classification. Similarly, we use support vector machine also for classification. So let's go through it. So support vector machine is supervised learning algorithms. We already know what is supervised learning. The data set is given along with its label, right? And the machine is made to learn using this data set. So it's a supervised learning algorithm which is used for classification as well as regression problems. The goal of the SVM algorithm is to create the best line or the decision boundary that can segregate n-dimensional space into classes so that one can easily put the new data point in the correct category in the future. Right? So the best decision boundary is called a hyperplane. So what we are doing, we are taking a data set, putting a line in between so that the data set gets classified into two distinct classes. So SVM chooses the extreme points or the vectors that help in creating the hyperplane. These extreme cases are called support vectors. We'll see ahead, and hence algorithm is termed as support vector machine. Now consider the diagram in the following slide. There are two different categories that are classified using a decision boundary or hyperplane. So here we plot data items, right, as a point in n-dimensional space where n is the number of features we have or the attributes we have, with the value of each feature being the value of a particular coordinate. Then we perform classification by finding the hyperplane that differentiates between the two classes. Now this is a hyperplane, right? So what it does, it's a single line which is separating two data sets into two distinct categories or two distinct classes, right? So you can just see this is a straight line. We call it as a hyperplane, and there are two supporting hyperplanes, right? One is positive hyperplane, another one is negative hyperplane. And the data points which lie on the supporting hyperplanes, we call them as support vectors. Fine. The data points which lie nearer to the supporting hyperplanes, we call them as support vectors. Now, what is our goal? Our goal is to maximize the margin. So what margin you need to maximize? You need to maximize the distance between two classes, right? So you need to put a line that is a decision boundary or hyperplane in such a way that the distance between two support vectors is maximum, right? So you can see the maximum margin, and this is maximum margin hyperplane. Fine. Now SVM can also be used for face detection, image classification, text categorization, etc. Now, to separate two classes of data points, there are many possible hyperplanes that could be chosen. Right? There are many possible hyperplanes that can be chosen. Our objective is to find a plane that has maximum margin, that is the maximum distance between the data points. Now, if you can look at it, these two data sets can be separated either using this line, either using this line, this line. All these lines are clearly classifying these data sets. But what we need to maximize the margin distance, right? So we select this hyperplane or a decision line, what you can say, which will maximize the difference between these data sets or these two class categories. Is it fine? So maximizing the margin distance provides some reinforcement so that future data points can be classified with more confidence. I hope hyperplane is clear. This is the hyperplane. These are the supporting hyperplanes. These are the support vectors, right? And you can classify the data using number of hyperplanes, right? What we do, we select the hyperplane which gives you the maximum margin between two set of classes. Now, hyperplanes are decision boundaries that help you classify the data points, right? Now, data points either falling on the either side of the hyperplane can be attributed into two different classes. Also, the dimension of the hyperplane depends on the number of features. If the number of input feature is 2, then the hyperplane is just a line. It is 2, the hyperplane is just a line, right? If the number of input feature is 3, then the hyperplane becomes a two-dimensional plane. You can see this. Hyperplane becomes two-dimensional plane, and it becomes difficult to imagine when the number of features exceeds 3. Right? This is a hyperplane for dimension for 3 features. Fine. Now, support vectors. Right? Now, support vectors are the data points that are closer to the hyperplane and influence the position and orientation of the hyperplane. Now, data support vectors are the data points. These are the support vectors, right? These are the data points which are closer to the hyperplane. You can just see compared to all the data set. These are the one which are closer to the hyperplane, and they influence the position of the hyperplane. Now, using these support vectors, what we do, we need to maximize the margin of the classifier. Right? If you look at the same data set here, you can classify it like this also. You can have a hyperplane like this also. But what it is, it will give you small margin. What we need large margin so that the classification of the future data sets becomes easy and the classifier is perfect. Fine. So deleting the support vectors will change the position of the hyperplane, and these are the points that help to build your SVM. Is it fine? These two data sets can be classified using this hyperplane also, but we don't select this. Why? Because the margin is small between two classes. This is a support vector, this is a support vector. We select this hyperplane because what it does, it maximizes the margin between two classes. Now, we understood the process of classifying or segregating two classes with a hyperplane that is a single line. Now, how do you identify which is the right hyperplane or which one we should select? So let us look at some scenarios. So this is case 1. Here we have three hyperplanes A, B and C. Now identify the right hyperplane to classify the star and the circles. Just look at the diagram carefully and let me know which is the correct one. Right? What you need to remember here, the hyperplane which segregates two classes better should be selected. Now, if you look at A, right, it is not classifying it that properly. You can see there is misclassification of circles lying on this side where the stars are classified. If you look at C, again there is a misclassification here. Circles are belonging to this side of the class rather than this side. So which is the correct one? If you look at the hyperplane B, it is clearly classifying the circles and the stars distinctly. Is it fine? Now look at case 2 here. Here what we already have three hyperplanes here. A, B and C, and all are segregating the classes well. Now how can we identify the right hyperplane? Whether B is good, C is good or A is good? All are clearly classifying the data uniquely in fact. So what we need is we need to maximize the distance between the nearest data points. Either class and hyperplane will help us to decide the right hyperplane. So what we need, the maximum margin between these two classes will give us the right hyperplane. So let's look at, so the distance is called as margin, and let's look how it can be done. If I select B, then what is the margin here? Margin is 2 less. If I select A, margin is 2 less here, right? But if I select C, it has optimum margin on both the sides, right? So the correct hyperplane to select to classify this data will be hyperplane C. Now, look at this. Now identify which is a right hyperplane. You might think B as a right hyperplane. Why? Because the maximum margin on both the sides. Yes or no? Right? But SVM doesn't think this way. When SVM does the classification, the first thing what it thinks about is perfect classification of the data set. Because if I select B, star is lying out this side. It belongs to this data set, but it is lying this side. So this is misclassified. So B cannot be selected. The right hyperplane is A. Why? Because first thing is the accuracy of classification, and then second thing is the maximization of the bond. So A is a proper hyperplane. Now if you look at case 4, fine. Now I am unable to segregate the two classes using a straight line. as one of the star lies in the territory of other class. You can just see. Like I can draw a straight line, but still star lies on this side. Yes or no? Now, so one star at the other end is like outlier. For a star class, it is an outlier. It doesn't belong to this class, though it is a star, right? So what SVM does is it ignores the outliers and finds the hyperplane that has the maximum margin. So this is ignored as an outlier and this is selected as a hyperplane. Fine. Now look at this class. Can you find a single line to segregate these two classes? So how will SVM do this? Right? We can't have a linear hyperplane between these two classes. So to solve this problem, it adds some additional features, right? So here we'll add a new feature z, which is x square plus y square. Now let's plot the data on the x-axis and z. Fine. So in the above plot, what you see, all values for z, hmm, would be positive always. Why? Because z is the squared sum of both x and y. In the original plot, red circle appeared closer to the origin of x and y axis, leading to the lower value of z, and star relatively away from the original result to higher value of z. Right? So in the SVM classifier, it is easy to have a linear hyperplane between two classes, but another question which arises is, should we need to add this feature manually to have a hyperplane? No. SVM algorithm has a technique, what we call it as kernel trick. So what is this kernel trick? It is a function that takes low dimensional input space and transfers it into higher dimensional space. It converts not separable or non-separable problem to separable problem. It is mostly useful in non-linear separation problems. It does some extremely complex data transformations and then finds out the process to separate the data based on the labels or the outputs we have defined. That's the class labels. When we look at the hyperplane in original input space, it looks like a circle. Yes or no? So this is possible, but this is a non-linear SVM. So this is also a type of classification which is not linear because you cannot draw a straight line. This is by putting a circle around the data points. Let us revise two important concepts of support vector machine, that is hyperplane and support vectors. So there can be multiple lines, we already seen, or decision boundaries to segregate the classes in n-dimensional space, but we need to find out the best decision boundary that helps to classify the data points, and this boundary we call it as hyperplane of SVM. The dimensions of the hyperplane depend on the features present in the data set, which means if there are two features, then hyperplane will be straight line. If there are three features, then hyperplane will be a two-dimension plane, as we already seen in the previous slides. You always create a hyperplane that has maximum margin, which means the maximum distance between the data points, between two classes, right? Now, what are support vectors? The data points or the vectors that are the closest to the hyperplane and affect the position of the hyperplane are termed as support vectors. Now, there are two types of SVMs. We have linear SVM. It is used for linearly separable data, which means if a data set can be classified into two classes by using a single straight line, then such data is termed as linearly separable data, and we call the classifier as linear SVM classifier. Non-linear SVM, it is used for non-linearly separable data, which means if the data set cannot be classified by using a straight line, then such data is termed as non-linear data, and classifier used, we call it as non-linear SVM. Now, the working of SVM algorithm can be understood by using an example. Suppose we have a data set. It has two tags, green and blue, right? It has two tags, green and blue, and the data set had two features, x1 and x2. If you want a classifier that can classify the pairs x1, x2 of coordinates in either green or blue, we can just directly have a straight line. So just a straight line, we can directly classify these two classes. So this is a linear classifier where a single straight line, that is a hyperplane, can classify the data. In case of non-linear, the data is non-linear arranged, then we can separate it by using, we cannot separate it using a straight line. So what we do, we cannot draw a straight line also. To look at the images here, right? So to separate these data points, we need to add one more dimension. For linear data, we have used two dimension x and y. So for the non-linear data, as we already seen previously, the same equation again, z is equal to x square plus y square, where the value of z will always be positive. So by adding the third dimension, the sample space will look below as below. So this is original, and this is after applying the third dimension z. Now, don't you think it can be separated using a single straight line, a hyperplane, right? So look at this. So now SVM will divide the data set into classes in the following way. So this is the best hyperplane. Since we are in 3D space, hence it looks like a plane parallel to the x-axis. If we convert into 2D space with z is equal to 1, then it will become as this as a best hyperplane, right? And the radius, so we get a circumference of the radius 1 in the case of non-linear data. I hope the concepts are a bit clear. Now, getting into an informal definition of margin, we can say that the shortest distance from a hyperplane to one side of its margin is equal to the shortest distance from the hyperplane to the other side of its margin, right? One side of the margin to the other side of the margin. Whereas the sides of the margin are parallel to the hyperplane. You can see the sides of the margin are parallel to the hyperplane. When dealing with the maximum marginal hyperplane, I'll be calling it as MMH, maximum marginal hyperplane. This distance is in fact the shortest from the MMH to the closest training tuple of the either class. So this is the closest training tuple of the either class, right? So a separating hyperplane, we can write it in the form of a formula W into X plus B equal to 0. So what is W here? W is a vector, weight vector. W1, W2 till Wn. N is the number of attributes and B is the bias. Now to add some visualization, let's consider two input attributes A1 and A2. Now training tuples are 2D, that is X is equal to X1 and X2, where X1 and X2 are the values of the attributes A1 and A2 respectively for X. Now consider B as an additional weight, that is our bias having the weight as W0. Now the same above equation we can rewrite as W0 plus W1 into X1 plus W2 into X2. Now here we know W1 is the weight associated with the input X1, W2 is the weight associated with the input X2, and W0 is the weight of the bias. Right. Now, does any point that lies above the separating hyperplane satisfies W0 plus W1 into X1 plus W2 into X2 greater than 0, right? Then it is positive, right? It's classified as, it belongs to positive hyperplane, this side of the class, right? Similarly, any point that lies below the separating hyperplane, so this is above the separating hyperplane and this is below the separating hyperplane, then the formula will be W0 plus W1 X1 plus W2 X2 less than 0. The value is negative here, value is positive, right? So positive hyperplane and negative hyperplane. The weights can be adjusted so that the hyperplanes defining the sides of the margin can be written as H1, there is a upper hyperplane, that is positive hyperplane, that is W0 plus W1 X1 plus W2 X2 greater than equal to 1 for Yi is equal to plus 1, that is positive hyperplane. Now W0 plus W1 X1 plus W2 X2 less than equal to minus 1 for Yi is equal to minus, that is it belongs to negative hyperplane. That is if any tuple that falls on or above H1 belongs to class plus 1 and any tuple that falls on or below H2 belongs to class minus 1. Now we can combine these two inequalities of the above equation, and what we get, yi of w1, right, w0 plus w1 into x1 plus w2 into x2 greater than or equal to 1 for all I. Fine. Now the distance from the separating hyperplane to any point on h1 is 1 by Euclidean norm of w, right? By definition, this is equal to the distance from any point on h2 to the separating hyperplane. Therefore, the maximal margin is 2 by Euclidean norm of w, where w is nothing but the weight. Right? Now, once you have found the support vector and MMH, remember the support vector defines the MMH, that is maximal margin hyperplane. We have trained support vector machine. So the support vector machine is trained now. Now the MMH is a linear class boundary, and so the corresponding SVM can be used to classify linearly separable data. So once I've got the trained support vector machine, now how do I use it to test the tuples, to classify the training data or the test data? So based on the Lagrangian formulation, the MMH can be written as the decision boundary. So this is the formula, right, which is based on Lagrangian formulation. Right? So here yi is the class label of the support vector xi. So this is our input xi. What we are doing is we are trying to check its class label, whether it is correctly classified or not. So this is the input, this is the output, right? Now xt is the test tuple. Now alpha I and b0 are the numeric parameters that are determined automatically by the optimization or SVM algorithm. Note that alpha I are the Lagrangian multipliers. L is the number of support vectors. For linearly separable data, the support vectors are a subset of the actual training tuples. Fine. Now given a test tuple xt, we plug in into the above equation and then check to see the sign of the result. If this tells us on which side of the hyperplane the test tuple falls, right? If the sign is positive, then xt falls on or above the MMH, that is maximum margin hyperplane. So the SVM predicts that st belongs to class +1. If the sign is negative, then xt falls on or below the MMH, and the class prediction is -1. The Lagrangian formulation of the problem contains a dot product. You can see here a dot product between the support vector xi and the test tuple xt. This will prove very useful for finding the MMH and support vectors for the case when the given data are non-linearly separable. Fine. Now there are few points what you should remember. The complexity of the learned classifier is characterized by the number of support vectors rather than the dimensionality of the data. Hence, SVM tend to be less prone to overfitting than some other methods like neural network. We prone to have overfitting, right? But SVM doesn't allow this. The support vectors are the essential or critical training tuples. Remember, support vectors are the points which lie nearer to the hyperplane. They lie closest to the decision boundary. If all other training tuples were removed and training were repeated, the same separating hyperplane would be found. Now, number of support vectors found can be used to compute an upper bound on the expected error rate of the SVM classifier, which is independent of the data dimensionality. This is the biggest advantage of SVM. So SVM with a small number of support vectors can have good generalization even when the dimensionality of the data is high. Let us look at some good features. It works really well with a clear margin of separation. You can directly draw a straight line to segregate the classes. It is effective in high dimensional spaces. It is effective in cases where the number of dimensions is greater than the number of samples. It uses a subset of training points in the decision function called support vectors. So it is also memory efficient. Why? Because it is not using the whole data set, it is using support vectors. So what are the limitations? It doesn't perform well when we have large data set because the required time is higher. It also doesn't perform very well when the data set has more noise, that is target classes are overlapping. Thank you. I hope the concept is a bit clear. These are the references what I used to prepare my lecture. Thank you. Stay home, stay safe.